Next up, let's return to the problem of copying a list now that we've learned about recursion. So we saw in a previous chapter that when we copy a list by just assigning one list to another, we end up making an alias. So if I say x equals some list and then y equals x, then y and x are pointing at the same object in memory. To get around this, we created a function called copyList, which did a shallow copy of our list. It made a brand new list in memory, and then one by one went through the elements, copying those over into the new list, which worked very well so long as our lists were flat, that is to say one-dimensional lists. But as soon as we had 2D lists, or possibly even more, the problem was when we copied those elements, we were copying references to the nested lists. Now we got around that for 2D lists by making a 2D copy, but then if we have a 3D list, the same problem persists. In order to have an arbitrarily deep copy, we need to be able to apply this shallow copy idea at any level of our list. So we scan through our list, and if the item itself, the elements in that list, are themselves lists, then we need to apply this shallow copy to those lists. And if those lists items are also lists, then we need to do that at the next level down as well. So let's, before we get to solving this problem, recap where we were with the problem. So I've written a copy of our function shallow copy here, which resembles the code we developed in a previous chapter. So this function takes in some list, creates a brand new list, and then copies each individual element from our input into our output list. So what we're left with is two separate spaces in memory with two copies of the same set of values. So two lists that look the same but are stored separately. So I could run this. I could say python-i deep copy. Deep copy is the name of the file. We're still looking at the shallow copy function here. And then I can create a list. So I'll say x equals 4721634. And then I'll say y equals shallow copy of x. And now x and y look the same. They have the same values, but they are not the same item in memory. And this was fine when we had flat lists. Everything seems to work. But now if I make a nested list, so I'll just add some extra brackets here, and say y equals shallow copy of x again. Now they look the same, so they're equivalent. And they're not the same list because we shallow copied that top level list. But what about their elements? If I say x at 0 is y at 0, that part's true. So even though the top level list is two separate entities, the elements in that top level list are addresses to these nested lists, and they're the same addresses, so they're the same non-distinct sublists. Which means if I say x at 0, 0 equals 100, so I change the first element in x, that changes in y as well. The problem here is our copy function doesn't work for nested lists. We saw before if we have a shallow copy on a list, we end up making a new copy of the list, but then the values we copy over are these original pointers. So it would point back up to this top level list. What we'd like to do instead is make new lists for each of these. So create a brand new list for each one of our sublists, and then copy the values over when they're primitive elements. So copy the A and the B and the C over. Repeating that for every element in our original list that itself is a list. Which is to say, in order to do a deep copy, we have to take this idea of the shallow copy and extend it into the actual copying process. Instead of just copying the elements over, we have to check, is this element a list or is it a primitive element? If it's a list, then we'll apply this shallow copy to each element in that list. If it's a primitive element, then we can just copy it over. Which is to say, we need recursion to do a proper deep copy. So the base case of this recursion would just be copying primitive elements over, and the recursive case would be if our elements themselves are lists, then we'll use a call to this copying function to copy those elements. So let's return to our code here. I'll say def deep copy, given some list. So this copies the elements of a list into a new distinct list, but it does so recursively such that any nested lists are copied instead of shared. Okay, so the basic structure of this code is the same as our shallow copy. We start with some empty list, and when we're done, we will return that list. Now we also need to go through each element in our list. So we'll say for element in our upper level list, our top level list. Because remember, this deep copy can work on a shallow list as well. So in the case where all of the elements are primitive, then this is a very simple thing to do, and will in effect be the same as the code above us. But now if an element is not a primitive element, in this case if an element is a list, then we need to call this deep copy function to duplicate that nested list, and then we'll assign that copied element into our copied list. So we have an element in our list. It might be a primitive and it might be a list. Let's do some type checking to see if it's a list. So we'll say if the type of our element is equal to a list. Now how do you get the type of a list? If you don't know the term for it, you can just say the type of the empty list. The type of empty list is of type list. So this will be if the element has the same type as the empty list, which means if our element is a list, then we'll deep copy that element. Right? We'll call our copy function recursively. So we'll call this the element copy, and that is equal to deep copy, the name of our function, of our element. Since we've just determined that this element is a list, we can apply this deep copy function to lists. So we'll pass this element and get a copy of it. And what we'll have back, assuming everything else works correctly, is a unique instance of a list that looks the same. So it has the same values. So if this element is now a copied list, we need to now make sure it goes into the upper level list. So we say copy.append our LE copy. So note we have our recursive case here. So for each one of the elements in our list, if it's a list, then we'll deep copy it as well. Note that jumps back to the top of this. It makes a brand new list and goes through each element in that list, which is one of our sublists now. If one of those is a list, then it will recursively repeat this. Now, we are not likely to have infinitely deep lists. This could be a problem if we have lists that are more than 1,000 levels deep. Note that's not more than 1,000 elements, but more than 1,000 nestings of lists. So we have a list of a list of a list of a list of a list 1,000 times, then our recursion would be a problem. Other than that, this should work out fine. And I think it would be pretty hard to create a list like that. And as I mentioned when we were first discussing multi-dimensional lists, really if your dimensions go above 2 or 3, you should start considering, is there a more efficient design for my data structure? Okay, so we call deep copy on our nested list. It gives us back a unique instance or a unique copy of that nested list with all the same elements, which themselves might be lists, but those are all now also deep copied. So we'll take that copy, we'll append it as the element, as a unique element in whatever list we're currently in. And then we'll go on to the next element. If that's also a list, then we'll deep copy. If that next element happens to be a primitive though, we need our base case. If that element is a primitive, then all we need to do is just copy it over. We don't have to worry about any sort of depth to it. So we can just say copy.append LE, just like we did in our previous shallow copy function. So ignoring this, and I'm just going to collapse that for now. Ignoring this line here, the rest of this code is pretty much exactly what we had before. Create a new list, go through each element, copy them over, and return that copy. The only difference is if the element that we're looking at is a list, then we'll call deep copy on it. And if we know that function works, we don't even have to look any further than that. That gives us back a deep copy. We'll append that. Now, in order for that to work, we have the rest of this definition. But in order to describe that definition, you don't have to describe all the stages of the recursion. You can just assume this function works and then develop it at the top level. Right? So if we know deep copy works, which we're in the process of doing, then this will give us back the correct version of a copy, and we'll just append that. And now in order to make that the correct version of the copy, we go through, we make sure we have our base case, our recursive case, and something in our recursive case that's making it smaller and smaller. Now in this case, we're not shrinking our list at all. So what's the step? What's making our problem a smaller instance of that problem each time through? And this is what I was saying, the depth of our nesting of our lists has to be limited. There's just no way we can create an infinitely deep list in Python. So what that means is each time we're saying for LE in list, we're peeling off one layer of that nesting. So this is the part that's actually stepping through the size of our problem. If the size of this problem could be described as the number of levels of lists, so the number of dimensions in our list, this is reducing one of those dimensions. It's saying take one of the elements out of the list, and then if that happens to be a list, treat it as such, but we're now treating one level deeper. So when we do that, we'll then reduce another dimension, until eventually we're not in a list, so we reach the base case. So let's put this here, base case. I'll describe this as well. This is the step. Remove one dimension from the list. So it's removing one element from the list, but that element is a dimension lower, you could say. And then our recursive case, where we're just calling deep copy on those elements. So we're going to run all this same code. So we're going to create a copy of x, and we'll check to make sure that we are cloning x, so all the values are getting copied through, that the top levels are distinct, and that the nested levels are distinct. All right, let's save and test our code. So clear this up, and we'll say Python. I'll do -i so I can type things. -i deepcopy.py. So let's make a list x, and I'll do a 3D list here. So 3 starting brackets, and I'll say 1, 2, 3, 4. That'll be my first list. And the next one will be 4, 5, 6, 7, 8. And then I'll even put one at the second dimension here. There's that. And that's the whole list. Okay, so we have a 3-dimensional list. At the top level, it has 2 elements, 1 and 2. Inside that first element, there is 2 elements as well, 1 and 2. And then inside that first element, there are 2 elements, etc., etc. I'll let you walk through the rest. So there's x, and we will now say y equals deep copy of x. So this is x, this is y. X is equal to y. They still have all the same elements in all the same order. X is y is false, and that's because just this top level, we said create a new copy, and that's what we're returning. But now the trick was, when we were copying the individual elements over, we had to make sure that those were copied correctly so as to not create aliases. So we could say x at 0 is y at 0, and this should be false as well. And that's good. And we can say the same thing another layer deeper. X at 0, 0 is y at 0, 0. That's also false, which means if I say x at 0, 0 equals 100, x has changed, but y has not. So using recursion, we created 2 distinct lists that are distinct no matter the dimension. All the way down, there are no shared pointers. Note that solving this problem without recursion would be quite a bit harder.